With independent groups designs, we're talking about our first detailed discussion of experiments. So remember that with an experiment, you have an independent variable that is manipulated and a dependent variable that's measured. The outcome variable, the independent variable is the cause, and the dependent variable is the effect. We're going to talk about a couple of different types of experiments, but we start with independent groups designs, and what makes them distinct is that you have different people in each condition of the independent variable. So you have one group that gets one version of the independent variable, a second group of different people who get the other. I'm going to be focusing on the analysis because it's the most complex part once you get the independent and dependent variable part of it. And there are three main steps to analyzing the experimental design: checking the data, making sure everything looks okay, describing the results using descriptive statistics that just tell you in general what the variables look like, and then confirming what the data. In terms of descriptive statistics, the mean is the most common one. The mean is a measure of central tendency. It tells you about the average score. And again, with an experiment, we're talking about the average score on our dependent variable or our outcome variable. For an experiment, we want to know the difference between each condition. So what is the average score for people who got condition A, and what's the average score for people who got condition B? So if I'm interested in whether Advil relieves headaches, I might have two conditions: one condition that takes Advil, one condition that does not take Advil, and I measure headaches. So Advil would be my independent variable, headaches would be my dependent variable. What I can get is I can get a mean, headaches or pain would be my dependent variable. I could get a mean of pain for my Advil group and for my no Advil group. The problem is, say my mean pain for my Advil group is a 4 and my mean pain for my no Advil group is an 8. Is that a meaningful difference? And that's where we get to more complex statistics, which we'll talk about in a second. The standard deviation is a spread of variability. What it tells you is about how far each group is on average from the mean, or how far each individual is on average from the mean. For example, this is a study of the hours of sleep that students got before a 9 a.m. class and a 10 a.m. class. And what you can see is that there's variability in the scores between the 9 a.m. and 10 a.m. class, but there's much less. So in the 9 a.m. class, students got between 3 and 9 hours of sleep. If you look at the 11 a.m. class, students got between 0 and 13 hours of sleep. So there's much more variability. And this also is important in capturing the day. However, we're not just interested in our dependent variable. Remember that with an experiment, we want to know about the effect of the independent variable on the dependent variable. How did our manipulations affect the dependent variable? So one descriptive statistic that we can use to measure this is the effect size, which tells you about the strength of the relationship. The effect size is called Cohen's d. What we do to calculate Cohen's d is look at the treatment mean minus the control group mean and divide by the standard deviation. There's a standard set of guidelines for interpreting Cohen's d. A d of less than 0.2 is considered a small effect. 0.2 to 0.8 is considered a medium effect, and then above 0.8 is considered a large effect. Now, how we say this in words, it's very important that not just you understand that small, medium, and large, but you know how to say it in words. So let's say we're interested in the effect of tutoring on research methods grades. Our independent variable is going to be tutoring. We're manipulating whether or not students get tutoring and seeing how it affects grades. So if we have an effect size of, let's say, 0.4, which is a medium effect, we would say that our independent variable tutoring had a medium effect on grades. So that's the easiest way to talk about it. You can also use the second strategy, which is a little messier, but you can talk about which group is higher. So hypothetically, we might think that the tutoring group had a medium effect, was to a medium extent larger than the non-tutoring group in terms of. Okay, so with our descriptive statistics, we're just talking about what the data look like in general. But what we really want to know is there really a difference in the behavior based on the independent variable? Did the independent variable really work. Descriptive statistics can't tell us that. What we need for that is inferential statistics that help us confirm what the data reveal. They tell us, did the independent variable produce a reliable effect on the dependent variable? They can also answer questions as how likely that you get the findings that you got due to chance rather than the independent variable. It also tells us important things. So remember, when we're looking at an experiment, just like with the survey, we're going to take a sample of our population. So we want to know, does our sample's results generalize to the population? So we can also use inferential statistics to tell us about that. So confidence intervals are the first inferential statistic we're going to talk about. Remember, again, as I just said, that we have sample means that we've calculated, and they're only an estimate of the population mean. So we have a sample mean. We want to know what the true population mean is. We can use something called confidence intervals to tell us the range of values that we think contain the true population mean. We do this with some probability, usually 95%. And the way you calculate it is the confidence interval is equal to your group mean plus or minus 2 times the group standard deviation. So just to give you an example, let's say we did an experiment. We have 2 groups. Group 1 has a mean of 57 and group 2 has a mean of 49. I want to know, is there a real difference between the groups? Did my independent variable have an effect? Based just on these numbers, we can't necessarily know that. What we can do to help us answer that question, though, is to look at what's called a confidence interval. So what a confidence interval is the range of scores where we think the true population means lie. The means of 49 and 57 are means for a sample. We want to know the mean for the population. So by using that criteria, the formula that I gave you before, we calculate the confidence interval. And what we can see here is the confidence interval for group 1 is that we believe that the population is somewhere between 54 and 60. And for group 2, we believe that the population mean is somewhere between 45 and 53. We're 95% sure the population means are somewhere in there. This can help us to determine whether there's a because in order to determine whether there's a true difference or not, we can look at whether these confidence intervals overlap. What we can see by the red lines is that the confidence intervals do not overlap. What that means in terms of what we can conclude is that the groups are significantly different. And what this suggests is the independent variable had an effect on the dependent variable. Here's another example. What if it looked like this? Here we can see that the group 1's mean is 57 and group 2's mean is 53. We've got a confidence interval range of 54 to 60 and 49 to 57. And what you can see here is that there's a huge amount of overlap. There's 3 points worth of overlap. What this tells us is that those groups probably aren't very different because it's very likely that the population means overlap. So in order to draw conclusions from the confidence intervals, what we do is complete a confidence interval around the sample mean for each condition. If they do not overlap, it tells us that the independent variable had an effect on the dependent variable. The population means for the 2 conditions are likely different. If the mean of one group lies within another group, it tells us that the population means do not differ because they overlap. Null hypothesis significant testing is another strategy. And here we're looking at is the mean difference between conditions greater than what might be expected by chance. What we do in this kind of inferential statistic is we assume there are no effects. So we assume that there's no true difference between the groups. And given that there is no true difference, what is the probability or likelihood of observing the results we got? If that probability is really tiny, then we say that results are statistically significant or the independent variable had a significant effect on the dependent variable. So this is all based on what's called the null hypothesis. Now, typically, if you're looking at your research hypothesis, there's going to be a difference. We probably wouldn't do the study if we didn't expect a difference between the means, because the difference between the means would tell us that the independent variable had an effect on the dependent variable. Tutoring had an effect on research methods scores. For the sake of statistics, what we do is we ignore that, and we can't statistically test our research hypothesis. But what we can do is we can test the null hypothesis. We can see, assuming that there is no difference between the groups, which is the null hypothesis, how likely is it that you would get the result? So the null hypothesis is always that there is no difference, and that's the only thing we can actually do. So we start null hypothesis testing by assuming the null hypothesis is true. We start out saying, okay, let's assume there is no difference. Then we take a look at the population mean. So this is an example from the Schellenberg article that you're going to read. The average IQ for students who got no lessons was 103.3. The average IQ for students who had music lessons was 111.4. So the difference between the groups was 8.1. And what we want to know is the observed difference that we found bigger than what we'd expect, assuming the null hypothesis was true? So is this difference of 8.1 greater than what we get if in reality in the populations there really is no difference between the groups? There's a couple of steps here. Many of them I don't expect you to know how to do. So once you get your mean, you can compute an inferential statistic that is associated with the mean. You're not going to need to do this or to know which one is appropriate. What you do need to understand is that with each inferential statistic that you calculate, there's a specific probability associated of getting that statistic. What that probability is the likelihood of getting that statistic given that the null hypothesis is true. So how likely is it that you'd get this specific t-value if there really was no difference between the two groups? And then what you're going to do is look at that probability or likelihood and compare it to what's called an alpha or a level of significance. Typically, we set alpha at 0.05, which means that if the alpha is the p-value or the likelihood of getting that result if the null hypothesis was true. So if there's less than a 5% chance of getting that result if the null hypothesis was true, we say this is a significant difference. In contrast, if the p-value is bigger than 0.05, there's a 6 or more percent chance that we get these results by chance. We don't reject the null hypothesis. That means that we assume that there really is no true difference between the groups, and we conclude that the independent variable did not produce an effect on the dependent variable. If the p-value is less than 0.05, if there's less than a 5% chance that you would get these results due to chance, if the null hypothesis were true, you reject the null hypothesis. So remember, the null hypothesis is that there is no difference between the groups. If it's extremely unlikely that you get the results that you got due to chance, if there really is no difference between the groups, then we reject that and say, yes, there is a true difference between the groups. And that, because we're doing an experiment and manipulating things, with that we can make causal statements, such as music lessons cause differences in IQ scores. The final note is that it's important to remember that because we're basing everything off of the null hypothesis, we never actually know the truth. We can never do a study that assesses every single person in the population with perfect measures. So we make this decision based on probability, but we don't always know if we're right. And statisticians try to take that into account. So there's two things that play into account in terms of what inferential statistics can tell us. One is the experimenter's decision, the decision that you make. You decide whether to reject HO, which is the null hypothesis. If you reject the null hypothesis, you say there is a difference, or retain the null hypothesis and say that there is no difference between the groups. There's also, however, the actual situation. I've heard people call this what the recording angel knows. If the recording angel knows everything that's going on, knows the truth, what the real numbers are for the population, this would be what they know. The reality could be that there really is no effect, that there really is no difference between the groups, or the reality could be that there is an effect, that there is a true difference between the groups. So that gives us 4 possible decisions. One correct decision is that you retain the null hypothesis, you decide there is no difference between 2 groups, and in reality there is no difference between the 2 groups. Another correct decision is that you reject the null hypothesis and say that there is a difference between the 2 groups, and in reality there is a difference between the 2 groups. But there are also two mistakes that you can make. So one is called type 1 error. Type 1 error is you say that there was a difference between the groups, say that the independent variable had an effect on the dependent variable, when in reality, there really was no effect. The other kind of mistake that experimenters can make is that you retain the null hypothesis, so you say that there was no difference between the groups, when in fact there really is a difference between the groups. So it's just important to be aware of all of the possibilities, mistakes